In the magical world of computer science, we have these things called dynamic data structures, and like their name implies, these structures are dynamic. They aren't definite in their size and can change at any time. In C, this is possible by utilizing the heap inside the memory map. In order to understand the linked list in C, it's critical for us to know the difference between the two main memory spaces, those being the stack and the heap. The stack is static, and its size doesn't change all that much outside of the functions that are loading on it. When a function is called, a specific set of memory is carved out for that function. It won't grow and it won't shrink. The heap, on the other hand, can change its size however is needed at runtime, and it's this property that makes the linked list possible. Without having dynamic memory allocation, we wouldn't be able to create and insert nodes. Well, how do you make a node or something on the heap for that matter? The function malloc is going to be our best friend. Malloc roughly equates to memory allocate, and it allows us to carve out memory blocks on the heap. Malloc itself doesn't actually do anything, because we need to give it the size of what it should be working with, and we can do this by using the appropriately named function sizeof. Sizeof tells malloc how much space it should make on the heap. In this case, it's calculating how much space is needed for all of our variables inside our rideshare structure, which is, for all intents and purposes, a data type. Malloc can return one of two things when it's called. If everything goes well, it will return the memory address at the start of the memory block it just allocated. And if everything goes sideways, malloc will return null. If malloc returns null, that means it wasn't able to create a space in memory for whichever reason. That's not good. Even though a space in memory has been created, our data members have not been initialized or set to values that we want. Currently, they're full of hot garbage. In order to initialize our data members, we're going to need to utilize pointers. But before we start filling the data and creating new nodes, we need to create the head for our linked list. The head is the most important part of the linked list, and if we lose the head, we lose the list. By storing a pointer to the head address in main, we can keep track of the linked list at all times. Each node in the list contains a pointer to the next address where the next node is. This allows us to have a near indefinite number of nodes without having to keep track of them all. We only need to keep track of the head, and we can jump through the next pointers until we arrive at the node we want. In order to place new variables inside the data members, we're going to need to pass a double pointer to the head of the linked list to whatever setup function you're using. This double pointer will point to the pointer holding the address of the head. Why do we do this? Well, we do this because the head address could change. This is so the head address can change, but we can still access it without having to update all of our pointers. In order to access the data members and update them, you'll need to use the arrow notation. If the node we are accessing is on the same stack, then we'd use the dot operator. Each node contains a segment that points to the next node. If this was a double linked list, then there would be a segment pointing to the previous one as well. When malloc kicks out the address for the new node, it's important to save that address for the node because we'll need to update the previous node's next node pointer to the new address that malloc generated. And that's pretty much how the linked list works in C. Bye!